Hello everyone. So today we will discuss about uh, dynamic programming in sequence alignment, and let's start our topic. So dynamic methods are the methods which in which we break down a problem into subproblems and the use of the solutions for subproblems. So basically, we divide the problem into smaller subproblems and then find solutions for each of them, and then merge the solutions to get the other overall solution. So for a problem of size n, all subproblems of size 1 to n minus 1 are solved, like I said before. And then uh, and solutions are saved in a table from which the solutions for n is derived. Like I said, we find the solution for each subproblem and then we merge them into one solution. And dynamic methods are usually very exact. However, they can be very slow. For example, the smooth waterman algorithm used in bioinformatics for sequence alignment. The concept of dynamic programming, which come from dynamic methods, it is actually becoming coming from operational research, where it is commonly used to solve problems that can be divided into stages with the decisions required at each stage. A good generic example is the problem of finding the shortest path on a graph. If there are 2 points in a graph and you want to find which path is the shortest path, because there may exist multiple paths to from one point to another point. So you need to find which path is the shortest one. There can be multiple alternative routes to follow. So this problem can be one of the problem that can be solved by dynamic programming, and similar types of problem can be you can say solved by dynamic programming algorithms. The scenes are where to go next at each node. It is a characteristic that the scenes at in one stage transforms that state into a state in the next stage. Once that is done, from the viewpoint of the current state, the optimal decision for the remaining states does not depend on the previous states or decisions. Hence, it is not necessary to know how a node was reached, only that it was reached. So basically, we have multiple options for each path, and we decide on the basis of optimality that which path to follow, and ultimately we reach our end state. So to find, so in bioinformatics or in sequence alignment, we want to find matching in nucleotides and amino acids of these sequences. We normally use a dot plot method, but dot plot cannot capture the insertion, deletion, and gaps in the sequences. To deal with this situation, we modified the dot plot, because dot plot is very inefficient with the insertion, deletions, or gaps in the sequences. So we have to modify the dot plot methodology to deal with this problem. We represent the matching nucleotides with the +1, while gaps and substitution and insertions and mutations can be represented as -1 in the dot plot. So this is one way of doing this. Dynamic programming is an algorithmic technique used commonly in sequence analysis. Dynamic programming is used when recursion would be used, but would be inefficient because it would repeatedly solve the same subproblem. So these are some of the facts about why to use and not use a dot plot, and how it can be modified to tackle a problem of mismatching, particularly insertion, deletions, mutations, and substitutions. So some essentials about the dynamic programming. When we talk about compression of two sequences one by one, it need time and is computation expensive method. That's why we need algorithm. In algorithm, we calculate the step involved in sequence compression. For example, if we compare two sequences of length n, then it would be n square. And its order is O n square. This figure represents the insertion, deletion, and gaps, while plus one represents matching nucleotides or amino acids. One by one amino acid sequence compression is costly and time-consuming process. We minimize the cost with the help of algorithm. So you can see in this comparison, unlike a dot plot method, we have assigned plus one to each. You can say matching pair and the minus one for each mismatching, or you can say extension mission or gap that has been here. So dynamic programming helps us to reduce the computation cost in sequence comparisons, and it works on the method of scoring functions. So we always have a scoring function in dynamic programming because unlike dot plot, we need to have a scoring function because this is not straightforward method. We take into account the mismatching that is caused due to insertion deletions or mutations or substitutions or any gap inserted due to you can say substitution or you can say mutation as well. So basically, we have to score these changes in the sequence alignment accordingly. So, for example, we have, for example, we represent match is equal to plus A, mismatch is minus B, and gap is equal to minus C. Then the score is equal to the summation of all these three matrices. For example, here is an example sample alignment. All the alignments are done in diagonal way in dot plot matrix. For total score, we make calculations in diagonal way, and after calculation, best one is selected. So as we discussed previously in dot plots, and that there can be multiple alignments in the which can be diagonal in the dot plot. You can say alignment method, and we select the one which has a you can say maximum or best one score. So in this example, particularly, for example, we decide that we have this scoring scheme that we will assign 10 to matching and 2 to mismatching and gap penalty as 5. So let's say this alignment goes there. You can see there are 4 matches, so they have been assigned 10. Then there are multiple mismatches and there are gaps as well. So in total, the score is 11. So this is how we you calculate the score for one particular diagonal in the dot plot matrix when we because we are modifying the dot plot methodology to take into account the insertion, deletion, and substitution matrices as well. So basically, we in this way we can calculate the score for all other diagonals, and the score with the best one and the alignment with the best one will be our optimal alignment. When we apply to the dynamic programming algorithm to the sequence alignment, two varieties of this method are in use: Diriman and Wunsch, which is the global alignment algorithm, which builds up an alignment starting with easily achievable alignments of small subsequences. Then other one is Smith-Waterman, which is the local alignment algorithm that is similar in concept, except that it does not systematically move through the sequences from one end to the other, but compares subsequences anyway. So these are the two modes of applications of the DPA, dynamic programming algorithm. One is Waterman, the other is a global dynamic, which is a Needham merge. But the in-depth methodology is the same, which is the dynamic programming. There are also some heuristic algorithms. For example, BLAST and FASTA that are faster than dynamic programming algorithms. They look for matches for short sequences, which may be only a few nucleotides or amino acids long, that they then seek to extend. As with the DPAs, some kind of scoring systems has to be used to quantify the matches. So this is very important that unlike dot plots, we need to have a scoring system in a dynamic programming algorithms, because we need to quantify the amount or percentage, you can say, of the matches present in the in the alignment. So this is all for now, and for next we will see some algorithm. And yeah, thank you. Bye.